Hello there, welcome back. So in this module, we are going to see how to simulate the small signal AC response of a differential amplifier. So on your screen, we have this differential amplifier for which we have already performed DC operating point analysis, and we have also seen the time domain simulations for this amplifier. Now it's time to understand the Bode plot of this amplifier. So what I have done, as you can see, to the input, base input of transistor Q1, I have set a small signal AC voltage source with amplitude of 1 volts, and the DC value indicates the DC biasing at the base pin of the transistor. And if you can see that the phase of this signal is 0 degree. On the right side, I have same voltage source. If I right click, I show the DC value of 0 volts and the AC amplitude again the same. However, the phase is minus phase is 180 degree with respect to the previous input signal. So here in the time domain representation, you can say the small signal that is applied to the base pin of transistor Q1 will vary like this, and the small signal applied to the base of Q2 will vary like this. So they are signal of the same magnitude but opposite in phase, and for which you expect an amplification like this at the VO1. Let me draw it properly. At the VO1 and at the VO2. At the VO2. So we have seen this in our previous model. So if you are new to this, refer to that. And this transistor circuit is called as differential amplifier, which is perfectly operating with the DC bias point setup. We have seen that earlier. Now let us plot the Bode plot of that circuit. And to do so, we would have run the AC analysis. So right here, you can see I have the syntax for the circuit simulator .ac decade 1000 points run from 1 hertz to 100 megahertz. So I right click here and I show you the behavior, the edit simulation command. I'm computing the small signal AC behavior of the circuit linearized about its DC operating point. So type of sweep, I have chosen decade. Number of points are 1000. Start frequency is 1 and end frequency is 100 megahertz. So accordingly, when I put these parameters, the syntax is ready. .ac decade 1001 and 10 to the power 7. Click OK. And with that, we'll have two plots. One, the magnitude versus frequency, the magnitude of the gain or we can also have a plot of decibel, gain in dB versus frequency. And the second would be phase versus frequency. So let us simulate. I will click the simulate button here and I'm done with the waveform window, and now it's time to plot the signal. So here VO1, I will take the probe and it is asking me to uh, plot this one. Remember, on the extreme left down of your screen, you can see there is a instruction, click to plot VO of VO1. That is circuit simulator is prompting me to probe this voltage here, and DC operating point is also 1.38 volts. So I click here. Once I do that, I have this smooth curve where I see on the left y-axis the gain about 42 dB or 43 dB, which corresponds to the gain in magnitude. Let us right click here again on the y-axis and choose a linear, where I see is about 135. So output is, if I apply 1 volt, so the output will be 135 volts. That is how the gain is the ratio of output divided by input, I will have the gain of 135. So output will be 135 times higher than the input. And I again right click here and choose the decimal, for example, and that's it. I have this. Now from this I move ahead. It starts from almost DC and go forward till this 3 dB points. It's about 39 right here. So at this point, I see I have a frequency of about, let me see how much is that frequency there. Well, I have to take this up. Just a second, I am doing that for you. Yeah, so here I'm seeing I have at 39 dB, that is minus 3 dB point, I have a gain of about 3 megahertz, right? That is my, or in other words, I can just right click here and maybe draw or add the cursor there. For example, I will just click this V of n and then I would say to attach the cursor, click OK. And now you see here the one, and then I will just move this line from here till the line I want. Okay, it went again. So let's do that. So here it is. Attach cursor first and click here, and then from here you move the cursor where you want. So I want it to be 39 dB. So for that I will do that. So here it is. So now you can see from the table that is given here, the phase at this 3 dB point is 136 degree and the magnitude is this. But the most important part is at 4.10 megahertz is again dropping to minus 3 dB point. That is the maximum gain you can have for this circuit. Okay, and the phase shift is 180 degree starting from the DC, and at 3 dB point it goes about it has a phase shift about 136 degree. What about you plot the VO2 now? So come back here, and again the VO2 is a little bit less. That is again the gain for this, and the VO2 is how much it is. Let us do that. So what I'll do, I will just add plot pane and shift VO1 to upper plot and the VO2 to the bottom plot. So 3 dB points and everything gonna be same, and the magnitudes are same, in fact, not the less or more. So it is like right zoom, yeah, it's about 42, and here is also you have 42. Okay, so that's it. So that's how you can run your analysis for the Bode plot and simulate the frequency response. So hope you like this video, and if you did so, just subscribe to the channel, share with others, stay tuned for more.